So this is a video on working through the first derivative test in more practice sheet. So I'm guessing at this point most of you have done this sheet, but if you haven't, it'd be a good idea to do it. And you could do it while watching the video. So you could try the first one, watch the video, check yourself, try the second one, watch the video, etc. So we're going to find critical points, where it's increasing, decreasing, local mins, local max. In this first part, that's what we're doing. We're not going to do the second derivative. So this is the first derivative test. So we go f prime of x is equal to, in this case it would be negative 6 minus 6x. And of course we take that and set it equal to 0. Which means negative 6x would be equal to 6, which means x is equal to negative 1. So the first derivative test would look like this. I have a negative 1 on it. I plug something smaller than negative 1, like negative 2, in here, and into the derivative, and I get negative 6 plus 12, which is obviously positive. Then if I plug something to the right of negative 1, like 0, I plug a 0 in here, and I get a negative. So what does that tell me? As far as the intervals, it is increasing from negative infinity to negative 1 and decreasing from negative 1 to infinity. Local maximins, looks like there's only a maximum that occurs at negative 1. And of course, to find out what the y value is, I'd have to go back to the original function. So I'd have to find out what f of negative 1 is. And that would be 5 minus 6 times negative 1 minus 3 times negative 1 squared. So that would be 5 plus 6 minus 3. 11 minus 3 is 8. Oops. So I have a maximum at negative 1, 8, and it's increasing from negative infinity to negative 1 and decreasing from negative 1 to infinity. So this is the information. This is the first derivative test. That's evidence of the first derivative test. That and finding the derivative. So those are the two pieces that show me that you're using the first derivative test. And this is the information I get from the first derivative test. Okay, let's do another one. I would change this to 9 times x squared. Oops, a daisy. Minus 4x plus 7 to the negative 1 power. I think that's what I would do. That way I don't have to use the quotient rule. So then the derivative would be negative 9 times x squared minus 4x plus 7 to the negative 2 power times the derivative of the inside, which would be 2x minus 4. So then if I simplify that a little bit, that would be a negative 18x, negative 18x plus 36, because I'm multiplying the negative 9 through here, on top, and I have an x squared minus 4x plus 7 squared on the bottom. So the first derivative test, I'm looking for what makes the derivative undefined or 0. Well, nothing's going to make it undefined. Will something make it undefined? So the question is, does that have any roots? Okay, so if I take the x squared minus 4x plus 7 and try to solve it, I find out that the solution, set equals 0 and try to solve it. I find out the solutions are imaginary, so that means this bottom can't be made equal to 0. So I'm only looking for so there's no points of undefinedness for the first derivative. So I'm just going to solve this then, negative 18x plus 36 equal to 0, which means negative 18x is equal to negative 36, which means x is equal to 2. So my first derivative test is going to look like this. Little 2 sitting there. Now the bottom will always be positive, so I'm just plugging in numbers in here to find out whether it's negative or positive. And if I plug in 0, which is left of 2, I get positive. If I plug in something bigger than 2, like 100, I get clearly a negative because a negative 180 is bigger than 36. That'd be negative. So that tells me that it's decreasing from 2 to infinity, increasing from negative infinity to 2, and that there's a maximum at 2 comma something. Go back up here and plug in 2, and I get what? 9 over, that'd be 4 minus 8 is negative 4, negative 4 plus 7 is 3. Oh, 9 over 3, which of course would just be 3. And there we have it. Okay, let's see. So that's looks good there. We'll move it down to 3. And once again, we're going to take the derivative, of course. That's what we always do to begin with. And that would be 3e to the 3x plus 2 minus 3. We want to set that equal to 0. And then we end up with e to the 3x plus 2 is equal to 1, because I add 3 to both sides and divide by 3. And if you take the natural log of both sides, you get 3x plus 2 is equal to the natural log of 1, which is 0. That means that x is equal to negative 2/3. So that's the only entry into my first derivative test, negative 2/3, because it's not undefined anywhere. So now if I plug a negative number, like a negative 100 in here, that's going to cause me for this to be really big, and that thing is always positive. So that would be positive. If I plug 0 in here, I get, well, that's also positive, isn't it? Okay. So this thing is increasing all the time. Interesting. So do we have a maximum or a minimum? No. So if we say this thing is going to be increasing, I guess it's not all the time. It increases from negative infinity to negative 2/3, and then from negative 2/3 to positive infinity, because it's not increasing right there. So there must be a little flat spot there for a moment. All right. Moving right along. Now this one I've already done. I think we did this in class, so I'll just pause that there for a moment so you can see it. I actually went ahead and drew the graph. And we did the second derivative stuff, but so that's what that looks like. I move on to number 5. Take the derivative, and we get what? Negative 2/3 times 2x plus 5 to the negative 1/3 power times the derivative of 2x plus 5, which is 2. So that would be negative 4 over 3 times 2x plus 5 to the 1/3 power. And we want that to be equal to 0. Well, there's no way to make that equal to 0 because the top is always negative 4, which means we can't make it equal to 0. However, that is undefined, isn't it? It's undefined when the bottom is 0, which would mean when 2x plus 5 is equal to 0, that would make it undefined. So that means x is equal to negative 5/2. That's when it'd be undefined. So my my first derivative test would just have negative 5/2 here. And we got to check. So now if we look at this thing, the top is always negative 4. The bottom could change. So if I plug a negative number in here, or I'm sorry, if I put it like a large negative number in here, this negative 2 times a negative 100 is going to be negative. So that would be a negative over negative, which would give me a positive. If I plug in a number like 0 here, the bottom is positive, so I got a negative divided by a positive, which is a negative. So it looks like we have a maximum at negative 5/2, comma something, It looks like I'm increasing from negative infinity to negative 5 halves and decreasing from negative 5 halves to infinity. If we plug negative 5 halves in there, back to the original equation, we get 3 minus 0, because that's 0 there, right? So that would just be 3. So I have a max at negative 5 halves 3, and it's increasing up to that point and decreasing after that. Now this didn't ask me to find a second derivative, but I'm going to go ahead and do that one, this one, because it's kind of interesting. The second derivative of that, so let's see, the first derivative was negative 4 over 3 times 2x plus 5 to the 1/3 power. Okay, of course that's the same thing as, oops, there you go. That's the same thing as negative 4/3 times 2x plus 5 to the negative 1/3 power. So when I take the second derivative, in other words, I take the derivative of the first derivative, I multiply that by 3, it turns into positive 9/4 times 2x plus 5 to the negative 4/3 times 2. So then we have 8 over 9 times 2x plus 5 to the 4/3 power. And once again, there's no way to make the top 0. And also, once again, this thing is undefined at x equals negative 5 halves. So the second derivative test is going to look similar to the first derivative. But notice when I plug in numbers, the top is always positive and the bottom is always positive because there's 4th power here. So this is just always going to be positive. So that means it's concave up everywhere except for at negative 5 halves. So what ends up happening is you've got a graph that looks like this. Remember at negative 5 halves, 3, there's a high point, right? But instead of being a rounded off point, what happens is it comes up like this, hits it, and then comes back down like that. And we know that it does that because the concavity is supposed to be concave up. So you can see that these are concave ups, not concave downs. Okay, so that was kind of an interesting one. Okay, we got a couple more here, and I think I'll just do those and then offline and then turn the video back on. Okay, so here's the last couple ones that I did off video. So there's number 6. Found out that the derivative is equal to 0 at 1 and defined everywhere. So we just had this fairly simple first derivative test, and notice that it's plus on both sides, so it's always increasing except for that point. So it probably looks something like that. And then this one here is we set the derivative equals 0, got negative 1 and 4 as our roots, and that gives us a max and a min. And I guess I didn't finish this. It's increasing from negative infinity to negative 1, and from 4 to infinity, and it's decreasing from negative 1 to 4. All right.